All right, class, we're going to continue our notes here, just doing a few example problems. Starting out, we want to observe the chart to the right, and we're going to answer the following questions. Starting with part A, which graph represents the longest bond? I've given a little hint here that the bond length, don't forget that's referring to the x-axis. So which of these, A, B, C, or D, represents the longest bond? Pause the video and see if you can answer that question. The longest bond would be D, because it has the greatest internuclear distance. It's the farthest over on the x-axis when it is at its maximum negative potential energy. So the lowest negative potential energy way down here for each of these graphs, you want to compare which one is the farthest over to the right. That's your bond length. Which represents the shortest bond length? Again, on the x-axis. A is the shortest bond length. If you look at the bottom of that A graph, right here, it's further to the left than any of the others. So that would make this our shortest bond. Next questions are asking about bond energy. Which graph represents the strongest bond? We need to look at the y-axis, or the potential energy, to decide that. Which one has the strongest bond? Pause the video. C has the most negative potential energy, so it has the strongest bond. If we compare these, C is the one that has the most negative potential energy. That makes it the strongest bond. And you could probably guess from that which graph represents the weakest bond. That would be B, because it has the least negative potential energy. Take a note here that the negative potential energy is equal to attractive energy. For all of these, the net force for each point would be 0. At that point where it's at the lowest potential energy, or the most negative potential energy, the net force is 0 for each of those, but we're comparing their negative potential energies. The one with the most negative potential energy is the strongest bond. The one with the least negative potential energy is the weakest bond. Now let's talk about bond order. Types of covalent bonds and their bond orders. Well, the number of bonding electron pairs shared by two atoms in a molecule is what's known as the bond order. In other words, a single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. A single bond is 2 shared electrons represented by 1 line, bond order of 1. Double bond is represented by 2 lines, that's 4 shared electrons, bond order of 2. And a triple bond is 3 lines, 6 shared electrons, bond order of 3. You've got examples of compounds with single bonds here on the left. You can see each of those is just a line. And then the double bonds, compounds with double bonds in them. This one has only double bonds. This one has a double bond in the middle, and then these are single bonds. And then we've got triple bonds over here. You should be familiar with this from last year. All right, well, the diagrams here at least. The bond length is the distance between the nuclei of 2 bonded atoms, and the bond energy is the energy that is needed to break the bond. It's how tightly the atoms are held together. So the length, bond length, would be the distance between the atoms that are sharing electrons. The bond energy is the energy it would take to break that bond. Now let's look at this table over here on the left-hand side. Now, if we wanted to, let me highlight here. if I can. There we go. I want to highlight just our carbon-carbon bonds to start with. So this, and this. Okay, I want to compare those. Generally, the shorter the bond length, the greater the bond energy, and vice versa. Something that we should be aware of. If you have a shorter bond length, the bond energy will be greater. Another thing we can get from this, let's just compare those three that I just showed you. As we go from single bond to double bond to triple bond, what's happening to the energy? It looks like it's increasing. The energy is increasing. What's happening to the bond length? Well, it's decreasing. So bond length and bond energy are inversely related. And when the bond order increases, as I just said, going from single to double to triple bonds, while keeping the two elements the same, the bond length decreases and the bond energy increases. When one element involved in a bond changes, so this, let's see if we can highlight another couple elements, or types of elements. So let's say we're going to compare a carbon-carbon single bond and then a carbon-nitrogen single bond. Compare those two. We have to compare the radius of the elements. So if one of those elements is different, like carbon-carbon versus carbon-nitrogen, we got to think about the radius. So which one has a greater radius, carbon or nitrogen? Well, if you were to look at the periodic table, you would see that carbon is to the left of nitrogen in the same column. So that means that carbon has a larger radius than nitrogen does. So if nitrogen has a smaller radius, then that means a carbon and nitrogen bond could be closer together than a carbon-carbon bond because nitrogen is smaller. It's possible for them to get closer. And that is exactly what we see. Your carbon-carbon bond has 154 picometers. The carbon-nitrogen bond is 143 picometers. It's a closer bond. The element with a smaller radius causes the bond length to be shorter and the bond energy to be greater. Because they're closer together, they also have a stronger attraction, so the strength of that bond will be greater. All right, now let's look at a couple of examples that are just a kind of different. Okay. In this case, on the graph to the right, the energy profile for the CF bond is provided. So this is CF. I put the little piece of the periodic table here just for our use so that we could identify the elements we need to. It says to draw the energy profiles for the CBr bond. So we're comparing the element that's different between these two is bromine and fluorine. So I've got fluorine right here, and then bromine right here, and we need to compare their radius. Pause the video and try to answer this question. Comparing fluorine and bromine, fluorine has 2 shells and bromine has 4. Since bromine has 4 shells, that means it's a larger atom. The radius of fluorine is smaller than the radius of bromine. So as a result, the CF bond length will be shorter than the CBr bond length. So if we're just looking at the length, the bond length, which is the x-axis, then the little dip is going to be further to the left for fluorine. So fluorine will be further to the left. CBr would be farther to the right. Okay, so that's one thing that will be different. We also know that the CF bond energy will be stronger than CBr because CF, because they're closer together, there's a stronger attractive force between them, so the bond will be stronger. If the bond is stronger in CF, that means CF is going to have a deeper dip, which means CBr will not be as sharp or as low of a dip. So this is what you end up with. The bond length is further to the right. The bond energy is not as negative. Another example here, let's compare the CF bond, which is the one that's shown, to the CC bond. All right, so we've got to compare fluorine to carbon. Now, both fluorine and carbon have 2 energy shells, so they're not in different energy levels. They're not in a different row. They don't have a different number of energy levels. So we've got to think about the number of protons, or the effective nuclear charge. Fluorine has more protons than carbon, so the radius of fluorine will be less than the radius of carbon. From here, our logic is very similar to the last slide. The CF bond length will be shorter than the CC bond length. So as we're drawing the CC bond length, it's going to be a longer bond length than what we've got shown right now. So it'll be further to the right. The CF bond energy is stronger than the CC bond energy, so that means the CC bond energy will not be as strong. Potential energy will be more negative for CF and less negative for the CC bond. So it should be the dip in this potential energy diagram should be further to the right and higher up than what we see for the CF bond, just like we have right here. All right, on the graph on the right, the energy profile for the carbon-carbon single bond is provided. We want to draw energy profiles for the carbon-carbon double bond and the carbon-carbon triple bond. So this is the single bond. Where is the double bond going to appear? All 3 bonds involve the same elements. So what we need to know is as the bond order increases, so it goes from single to double to triple, as the bond order increases, the bond length shortens and the bond energy gets stronger. Bond length shortens, bond energy increases. So that means if we're just looking at the CC double bond, we're going to have a shorter bond length because it's a double bond, and it's going to be a stronger bond because it's a double bond. Okay, so it should be down and to the left a little bit. Because the potential energy is more negative, it'll be further down, and it'll be further over to the left because the bond length will be shorter. And that's what we see for CC double bond. And the CC triple bond, again, it's going to be the same trend. We get one more bond, the bond will be shorter and the bond will be stronger. And that's just what you see here. So that you should get something similar on this example. Go ahead and we're going to go ahead and stop the video here. This is the end of our notes. You should be able to complete the practice problems related to potential energy diagrams now.